Alright guys, today we are working in section 4.5. Section 4.5 is all about limits again. Now it's been a little while since we've devoted time specifically to limits, but this is a new type of limit we need to talk about. These are called limits at infinity. So today we're going to talk about things that look like this. Let's see here. Limits at infinity. Alright, what we're talking about is items that look like this. A limit as x approaches infinity of f of x. Or perhaps a limit as x approaches negative infinity of some function f of x. So previously, we've talked about limits a lot. Chapter 2 was all about limits. We always looked at the limit as x approached some finite number. Then we looked at one-sided limits, where x approached a finite number from the left or from the right. Here, we're looking at what happens as x increases without bound. That is, x goes off toward positive infinity. Or perhaps what happens as x decreases without bound and goes off toward negative infinity. Now what these limits do is allow us to get an idea of what the end behavior of a function is. End behavior. So these allow us to find end behavior. Now what do we mean by end behavior? Alright, end behavior is like what's happening way over to the left of a graph and way over to the right. So let's say we have some sort of function, it may be some sort of polynomial and doing all kinds of crazy stuff right here. But what's happening way over there, and maybe what's happening way over here? Is the function going off, in this case, toward positive infinity, going over there, and then maybe toward negative infinity in that direction? Or maybe is it a different function that looks like, say, let's see here, something like this. Kind of like a W. And so maybe it's going off toward positive infinity that way, and positive infinity this way. Or maybe is it some sort of function where it is going towards some horizontal asymptote. That is, it's going toward 0. Over here, and maybe going toward positive infinity this way. That would be like some sort of exponential equation, a function. So this is what we're talking about here. These limits right here allow us to analytically, that is via calculus, figure out what the end behavior of a graph is going to look like. Whether it's going to approach some sort of horizontal asymptote, whether or not it's going to go off toward positive infinity or negative infinity, that kind of thing. So this is kind of the last piece in us being able to graph functions by hand. So we've talked about maximums and minimums. We've talked about increasing and decreasing. We've talked about concavity, up and down. We've talked about inflection points. And now this is kind of the last piece that will allow us to figure out how to graph just, random functions by hand without the use of a graphing calculator. That's kind of the end goal currently, to be able to graph rational functions by hand. Different kind of modified logarithmic and exponential functions, stuff like that. That's where we're headed. In fact, after the lesson today, the next lesson will just be the culmination of all this. Nothing really new in the next lesson. It'll just be putting all of these techniques together to graph polynomials, exponentials, trig functions, all of that stuff by hand. So today we're just going to talk about how to find these limits, how to evaluate limits that look like this. Largely, there's some techniques obviously listed here on the left, but a lot of this can be done mentally by just thinking about what is happening with your function as x is either increasing or decreasing without bound. So let's just look at a few basic examples. Let's start off easy, and let's see what happens. Okay, let me back up just a little bit. First of all, let's just look at this definition of a horizontal asymptote, because a lot of times, the way you do find a horizontal asymptote is by looking at these limits at infinity. Okay, so it turns out if the limit exists here, that is, if we evaluate either this limit or this limit and get a finite number, then that means there is a horizontal asymptote at that finite number. So let's say you evaluate this limit as x approaches infinity and get 5 as your answer. That means there's a horizontal asymptote at 5. Or if you evaluate this limit right here and get -2, okay, or get 0, then that is your horizontal asymptote. Okay? So this is how we find horizontal asymptotes. It's also possible for these two limits not to exist. Like that's what's happening over here when you're going off towards positive infinity or negative infinity. It's possible to evaluate a limit at infinity and it turns out to be an infinite limit. Now I know that might sound crazy because I just had infinite in two different spots, but this is a limit at infinity, and it's possible for that to be an infinite limit. An infinite limit is when you take a limit and get an infinity or a negative infinity as your solution. That is like a specific type of does not exist limit. Okay, so let's like I said, let's jump in easy to start with and see what happens. So something easy like let's look at the limits as x approaches infinity. Oh, let's see, 3 over e to the x power. Okay? Now, you don't really need to there will be instances where we have to kind of rearrange this to get a better idea of what's going on. But for here, all we really need to do is think about what's happening on the numerator and what's happening on the denominator as x gets really big. You can make a table if you need to. You can make a table in your graphing calculator, clearly. That's the easiest way if you're having trouble and just kind of thinking about it in your head. But, at least if you're in my class for this chapter 4 test, you won't have a graphing calculator available to you, so you can make a table using just a regular scientific calculator that will be allowed. But I challenge you just to really think about in your head, or draw a couple figures out and think about what's happening on the numerator and denominator as x gets really big. For instance, what I'm saying here is that as x gets really, really big, 3 is not changing. The numerator is not changing at all. Okay? But as x gets really big, the denominator is getting massive. Like, let's just look at a quick little table. Okay, let's see. If we have x values and then f of x values. For instance, we could say, like, if x equals 0, then f of x equals what? F of x equals 3 over e to this 0 power, so that equals 3. Okay? If x equals, let's say, 100, okay? Well, we need a calculator for that. Actually, that might not even work in a calculator. So let me back up. Let me get a smaller x value. Let's see. Back up. Let's do 10. Okay? If we plug in a 10, we would have 3 over e to the 10th power. Now, I have no idea what that actual, what that is when you look at an approximation. Let's see real fast. E to the 10 power is about 22,000. So we would have 3 divided by 22,000 approximately. And that is going to be some crazy small number. For all practical purposes, approximately 0. As you keep getting bigger and bigger, 100, again, approximately 0. If you go to 1,000, this is what it means to say x is increasing without bound. X values are getting bigger and bigger, approximately 0. Okay? Because the denominator here is getting crazy big really fast, but the numerator is a constant. So this limit is equal to 0. And a lot of times we can just think through these in our head, or maybe make a quick table and maybe make a quick table to justify what we're thinking, make sure we're on the right track. But a lot of them are that simple. Some of them are not. We'll get to some more difficult ones, but a lot of them are just that simple. For instance, let's look at another one that's not too bad. Let's look at a one that's it's the difference of two functions. Let's look at the limit as x approaches infinity of 5 minus 2 over x squared. Oh, by the way, this right here means there's a horizontal asymptote at y equals 0. If we evaluate a limit at infinity, if we evaluate a limit at infinity and get a finite number, then there is a horizontal asymptote at that finite number. So here, this indicates to us that we have a horizontal asymptote at y equals 0. So essentially, the x-axis is a horizontal asymptote. Now, let's look at this one. Right here, we can use our rules of limits, our properties of limits, to kind of break this apart if you really want to. We could say this is equal to the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Now, let's think about what this means here. That's a constant function. That's just a horizontal line at 5. So this says, what is the limit of that horizontal line? That is, what is the trend in the y values? Well, clearly, that's just 5. The trend in the y values, there's only one possible y value here. And that y value is 5, no matter if your x value is 0, your x value is 100, or your x value is 1,000,000. The only possibility for your y values for this first limit is 5. So the limit is 5. Now over here, what is happening is x is getting really big. This is the situation just like we had in the previous example. The numerator is constant, it's just 2, but the denominator is x squared. So think about just what would happen if you plugged in maybe a 1 first. The result would be 2. Then if you plugged in a 5, you would have 2 divided by 25. If you plugged in a 10, you would have 2 divided by 100. If you plugged in 15, you would have 2 divided by 225. If you plugged in 17, you would have 2 divided by 343. If you plugged in bigger and bigger numbers, if you plugged in 100, you would have 2 divided by 100 squared. And all of these numbers are getting smaller and smaller. If you divided by 2, if you plugged in 1,000,000, you'd have 2 divided by 1,000,000 squared. Okay? So as x is getting really big here, this whole fraction is getting super small, getting closer and closer to 0. So we would say the limit is 0, but the solution in total is 5 minus 0, or 5. So this function right here has a horizontal asymptote. This solution means we have a horizontal asymptote at y equals 5. Again, if we get a finite solution here, that means that we have a horizontal asymptote at that point. Okay? Now, what about a rational function? Right here are the guidelines for how we deal with rational functions. Okay? So let's take a look real fast. Let's look at the limit. Let's look at the limit as x approaches infinity. Let's see, 2x minus 1 over 4x plus 5. Now, it turns out these guidelines right here should look very, very familiar to you. In fact, I just got through teaching my college algebra students 2 weeks ago these exact same properties, except the only difference is completely different book, completely different author, but the only difference is between the guidelines that we saw in our algebra book versus these guidelines we have in our calculus book is that here the word limit is replaced in the college algebra book with the words horizontal asymptote. So in a college algebra book, we would say if the degree of the numerator is less than the degree of the denominator, then there is a horizontal asymptote at y equals 0. We would say for item number 2, we would say in a college algebra textbook, we would say if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the leading coefficients. And for item 3 here, we would say if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. But here, in the calculus textbook, it's just couched in terms of the limit at infinity, but we know that limits at infinity are how we get horizontal asymptotes. So, if we remember those rules from algebra class, we could say automatically, oh, the degree of the numerator here is equal to the degree of the denominator here, so I know that the limit in this case is just the ratio of the leading coefficients, that is 2 over 4, which equals 1/2. Whereas the college algebra textbook didn't explain where the horizontal asymptote justified where it came from in terms of limits, now we're saying, okay, this limit here is equal to 1/2, which means there's a horizontal asymptote at y equals 1/2. Now, why is this true? Why does this make sense? It makes sense because in a rational function, think about what's like dominating the top and what's dominating the bottom. The greatest power of x, if there's multiple powers, like this is technically an x to the 0 power here, x to the 0 power, the greatest power of x is what's going to dominate the numerator and then dominate the denominator. So 2x is what's really going on the numerator, and 4x is what's really going on the numerator. So for all practical purposes, we could say that this rational function behaves for large values of x like 2x over 4x. And then we just reduce. 2x over 4x reduces to 2 over 4, which reduces to 1/2. So when you're dealing with rational functions, it's just important to realize that the highest power of x is what's going to dominate the numerator and then dominate the denominator. Okay, that's why we in our rules here, in our guidelines, we're saying look at the degree. Remember, the degree is the highest power of x. That's what degree is. So that's what we're looking at here: the highest power of x on the numerator and denominator. Again, these rational functions are really easy to deal with. Let's see. I mean, as long as you remember these guidelines here, of course. But that should be somewhere in the back of your head from a college algebra class. So let's say like the limit as x approaches, let's say negative infinity this time to make it a little more interesting. So this would be like end behavior to the left. Think about your graph way over here to the left for negative x values. And typically for these examples here, I just did positive infinity, so we were looking at the right-hand in behavior. But let's look at the left-hand in behavior of, let's just say, another rational function. Let's say, let's see here, negative, no, not negative, let's see, fraction. Let's say x squared plus 3x plus 2 over x to the 4th power plus 5. Okay? Now, this is a rational function. We have a polynomial on the top, a binomial on the bottom. All we have to consider is the degree of the top and the degree of the bottom. Okay? And here, the first guideline here, again, same thing as in college algebra, says that if the degree of the denominator is greater than the degree of the numerator, then this limit here equals 0. So it turns out that it really makes no difference if I'm looking at in this particular case, that is, it makes no difference if I'm looking at the left hand in behavior versus the right hand in behavior, because here there is a horizontal asymptote at 0, whether you're looking to the left or the right. Now, there can be two asymptotes. We'll look at an example of that in a few minutes, perhaps. But here there's just one horizontal asymptote. And I guess I should throw out there that if you're dealing with a rational function, your graph is not going to cross a horizontal asymptote. So keep that in mind as we move into our next lecture, when we're graphing these. That in general, you can pass over a horizontal asymptote. Like, we'll look at different functions, maybe like sine of 1 over x is a pretty classic example of a periodic function that has a horizontal asymptote at y equals 0, but passes over actually an infinite number of times, but the end behavior is what the horizontal asymptote speaks to more specifically. The end behavior of the function looks like y equals 0. But in this case, we have a rational function. A rational function is not going to cross over a horizontal asymptote. Now remember, a vertical asymptote, whether or not, whatever kind of function it is, a vertical asymptote is not going to be crossed by the graph. But a horizontal asymptote can be crossed by non-rational functions. Okay? Let's see here. What about a couple more examples of these rationals? Let's see. I mean, these are so easy. I hate to even really spend much time on them because they all are just using those exact same rules from algebra. Let's look at the limits as x approaches infinity. Let's see here. What about 3x to the 5th power plus 4x squared minus 2 over x to the 4th minus 5x squared plus pi. Just something kind of made up. Now here, notice what is the degree of the numerator and what is the degree of the denominator. The degree of the numerator is 5, the degree of the denominator is 4. Now we say here that the limit does not exist. This is kind of option 3 here. The degree of the numerator is greater than the degree of the denominator. Now why is that true? That's true because if you start plugging in big numbers, you're going to be raising, first of all, the limit is going to be dominated by this. Those are the largest powers. The limit's going to be dominated by those two. Okay? Now, we take a big number, raise it to the 5th power. That might not seem like a big difference, but it's going to be a lot bigger than that same number raised to the 4th power. A whole lot bigger. So the top here is growing at a much faster rate than the bottom, and so this limit does not exist. Now, we need to say, well, okay, it doesn't exist, but where is it going? Is it going off toward positive infinity? or is it going off toward negative infinity? Okay, so we have to think about this. If we take a really big positive number, raise it to the 5th power, and then divide by that really big same positive number raised to the 4th power, is the result going to be positive or negative? And I think clearly here we'll have all these terms be positive, so this is going off toward positive infinity. Again, I want to stress here, this limit does not exist. This solution here is a special type of DNE, does not exist. But this would be like the situation right here, where over here to the right, the limit is going off toward positive infinity. The right hand in behavior is going off toward positive infinity. Now, let's actually change that up a little bit. Let's not assume this, and let's say we're approaching negative infinity instead. Let's see how that might change the solution. So this would be left hand in behavior. Now, the general result of does not exist still applies. That is, we're going to be taking a number, raising it to the 5th power. That's going to be a much bigger result than that same number raised to the 4th power. But now let's think about, is this going to go off toward positive infinity or negative infinity? So if you take a negative number, let's just say a really big negative number, but any negative number, and you raise it to the 5th power, what is the result going to look like? Is it going to be a negative or positive number? Well, we all know that when you raise a negative number to an odd power, you get a negative result. So the numerator, if we plug in negative numbers, is going to be a really big negative number. And if we plug in a negative number to the 4th power, if we raise a negative number to the 4th power, what do we know the result's going to look like? It's going to be positive. So we're going to have a really big a really big negative number divided by a really big positive number, and that's going to result in a negative result, a negative number. So the limit to the left, that is, as x is decreasing without bound, I shouldn't say the limit to the left, but as we're going off to the left-hand side, as x is getting smaller, that is a bigger negative number, that limit is going off toward negative infinity. So this situation, now this is rational, so it wouldn't look like this in the middle here, but generally speaking, the end behavior of this rational function right here would be negative infinity over here to the left, but positive infinity over here to the right, much like this kind of yellowish function. Now, let me be clear, this rational function would not look like this in the middle, but the end behavior of this rational function would look something like this. Negative infinity way off to the left, and positive infinity way off to the right. Okay? Again, these are just special cases of the limit not existing. Okay? But this says specifically why the limit does not exist. So we call this an infinite limit. So this is what I said earlier when I said it's possible to have a limit at infinity be an infinite limit. So an infinite limit is when you take a limit and get a positive or negative infinity as your answer. Okay? Remember, that's just a special case of does not exist. And a limit at infinity is when you're looking at the limit as x increases or decreases without bound. That is, you're looking at the limit as x approaches negative infinity or positive infinity. So that's the distinction between a limit at infinity. This is what we're talking about here. A limit at infinity can have a finite answer. So 0 is a finite answer here. 5 was a finite answer here. 1/2 was a finite answer here. These are all limits at infinity with finite answers. But it's also possible for you to have a limit at infinity and get an infinite answer, which is called an infinite limit. Okay? And what we're doing here is we're trying to figure out the end behavior of these functions. So we've talked about rational functions. We've talked about just some basic functions. Let's talk about some trig functions. Okay? If we talk about trig functions, trig kind of freaks people out sometimes, but the same principles exist. Except we're not looking at we don't have necessarily a quick and easy test like those 3 guidelines with rational functions. We have to maybe be we have to be up polish our game up with our trig to make sure we understand what these basic trig functions look like graphically. What be brushed up on our unit circle, that kind of stuff. So let's see. Let's start off with easy trig limits first, and see what we can come up with. So let's look at the limits as x approaches infinity of really basic sine x. Okay? Now, we have to think to ourselves, and there's no trick here, we have to think to ourselves, what does this look like just in general? Okay? Well, in general, we know that sine looks like this. Starts at the origin. Well, it doesn't start at the origin, but we can start drawing it at the origin. And sine looks like this. And it keeps going on, following that same pattern. Now, of course, my drawing there is terrible, but you get the idea. We have, for a non-modified sine function like we have here, that's positive 1, and that's negative 1. So this function is bouncing back and forth between negative 1 and positive 1. Remember, the period is 2 pi, so every 2 pi units on the x-axis, the sine function is going to take on every possible value between negative 1 and positive 1. Okay? So as that x increases without bound, this graph is not approaching any horizontal asymptote. It's not approaching any one y value. It's going up to positive 1, then going down to negative 1, then going back up to positive 1, then going back down to negative 1, every 2 pi units. So we would say here that that limit does not exist because this is not, homing in on any one specific y value. Okay? This is bouncing back and forth between negative 1 and positive 1, not approaching anything specific. So we just would say this limit does not exist. Okay? Now, that's not to say that we're not going to have lots of trig limits that do have a finite solution and do have a solution, but this particular one here, and the same thing for cosine, does not exist. Okay? Because again, cosine would be doing the exact same thing. If you looked at the limit, well, it would be doing a very similar thing. We looked at the limit as, let's say, x approaches negative infinity of cosine x. Well, cosine x is, obviously really similar, except it starts, well, when we start drawing it, it's up here at the origin, has a value of 1. So like this. Oh, that's not a very pretty one. Well, it's not going to be pretty, but, you get the idea. You know what cosine looks like. Cosine, again, is bouncing back and forth between negative 1 and positive 1. Okay? So again, just like sine, here, if you look over, and why did I draw it here to the left? Because we're looking as x decreases. That is, as x is getting bigger and bigger negative. And again, it's bouncing back and forth between positive and negative infinity, which means the limit does not exist, which means there is no horizontal asymptote. Okay, no horizontal asymptote. Now, let's see here. What about if we look at some more complicated trig limits? Okay, some more complicated trig limits. Let's see here. Let's take a look at the limit. Oh, let's look as x approaches infinity of sine x, this time over x. Okay? Now, let's think to ourselves, what is happening here? Now, don't let this confuse you with the very similar limit we saw back in Chapter 2. Back in Chapter 2, we considered the limit of sine x over x as x approached 0. Okay? Now, we can actually solve this problem in a new way. I'll show you that in a sec, because we're going to have this. The one thing I haven't talked about as far as the theorems I had listed up there was a thing called L'Hopital's rule. So I'll talk in a few minutes about L'Hopital's rule, would help us evaluating this now that we know about derivatives. But now, for the moment, we're looking at the limit as x approaches infinity, not 0. So don't let that trip you up, because I know we did lots of limits that were similar to this, but we were looking at in Chapter 2 at least, not as x approached infinity, but as x approached 0. So now let's think about what's happening here as x approaches infinity. What does this limit look like, you think? Well, again, let's think about the numerator and think about the denominator. Now, we can't talk about the degree of the numerator versus the degree of the denominator, because the numerator is trigonometric, not a polynomial. Okay, so we have to think about this in terms of just what's going on here. Now, what do we know about sine? That's just a regular standard sine function. We know that its values range between -1 and +1. Range is between -1 and +1. So at the very least, this is -1. At the very most, it's +1. Even though x is increasing without bound. So x is getting huge, but sine of x at most is 1, and at least is -1. So this right here, the numerator is bounded between -1 and +1, but the denominator is unbounded. That is, the denominator is getting bigger and bigger and bigger and bigger. Okay? So this is getting bigger and bigger and bigger. Excuse me, this is getting bigger and bigger and bigger. This is staying between -1 and +1. So let's just say, for the sake of argument, that the top is -1. Now, it's not constant for sure, but we're going to have something like negative, as x gets really, really big, you're going to have stuff like -1, over a really huge number. Okay? For instance, like if you have, like sine of, let's see, if you plug in sine of, increment of 2 pi. So, 20,000 pi. Okay? If you substitute in here 20,000 pi, which is a big number, I suppose, you would have, oh, that's not good, because that's a 1. Let's put an increment of a different increment. Sorry about that. Pick up, do just a number here, a really big number. You're going to have some number between 0 and 1, excuse me, -1 and +1, divided by a really big number, and so the answer is going to result in 0. That is, the limit is going to be 0, because the bottom part, the denominator, is increasing without bound, but the numerator is stuck between -1 and +1. So that limit is 0, which means we have a horizontal asymptote at 0. Now, I should say, let's actually pull up a graph, because this is one of those instances where we might have a horizontal asymptote, yes, but the graph is sine of x divided by x. Zoom in here. Notice here that we have a horizontal asymptote. It's kind of hard to see. Let's see if I can make it a little bit brighter. Yeah. There's a horizontal asymptote at the origin at y equals 0, because that is what the end behavior of this function looks like. I mean, it almost looks like a straight horizontal line if you zoom out enough. But if you zoom in, notice that function is crossing over our horizontal asymptote. And that's fine with trig functions. That will happen a lot of times, actually. It won't happen with your rational functions, but it does happen with your trig functions. So the end behavior of this trig function, sine x over x, is approaching the horizontal asymptote y equals 0, really far off to the right and really far off to the left, but it doesn't necessarily mean that it's only, that there's not more interesting things going on closer to the origin. Right here, there's some curves here close to the origin, but as you get further away from the origin in both directions, the graph is going to level out closer and closer to the horizontal line y equals 0. Same thing like if we look at sine of 1 over x. Now we'll talk about this in just a second. Now we've actually seen this function back in chapter 2 because we talked about the limit here. It's even hard kind of for the calculator to render this because it's going to cross here close to the origin an infinite number of times. But see what happens as you get further away from the origin. As you get further away from the origin, this function is approaching the horizontal axis at the asymptote y equals 0. So there's crazy stuff happening close to the origin, but as you get further away from the origin, both in the left-hand direction and the right-hand direction, this function looks more and more like a horizontal line. That is, there's a horizontal asymptote at the origin. Now let's see why that might be true, just thinking about it analytically. Okay, so if we're going to look at the function, let's see here, the limit as x approaches, let's just say negative infinity this time, of sine 1 over x. Again, with a lot of these trig ones, you just really need to think about what's going on. Sometimes there'll be some like rearrangement, or I'll show you this new technique called L'Hopital's rule for some of these. But for some of the basic ones, you just need to think about what's going on. Think about what's happening as x is getting bigger and bigger and bigger, in this case in the negative direction. So you're looking at 1 divided by negative 10,000, then 1 divided by negative 100,000. Then 1 divided by negative 1,000,000. What is happening here in the argument as x in this case is decreasing without bound? Now, technically, remember, here's what we're doing. We have we had a theorem back in chapter 2 for composite functions, and we could say that this is equal to sine at the limit of 1 over, sine evaluated at the limit, make this a little bit bigger, the limit as x approaches negative infinity of 1 over x. We had that was a rule for composite functions. So essentially, we look at the limit of the inside function and evaluate that at the outside function. So what is this limit here? Okay? What's the limit as x is getting very, very, very big in a negative manner? Well, that's going to 0, right? So what's the sine of 0? Well, sine of 0 is 0, which means we have a horizontal asymptote at y equals 0. Exactly what we just saw looking at that graphically in Desmos. Okay, so again, with these simple trig limits, what you want to do is just think about what is happening as x gets bigger. Now, for some of the more complicated ones, you might need to do some rearranging. For instance, if we want to look at the limits, let's see, here's a nice one. As x approaches infinity, of x minus cosine x over x. Now, I can't really just look at that and figure out what's going on. We know, of course, cosine is ranging between -1 and +1. X is increasing without bound, and this is increasing without bound. So I would assume here that kind of x is dominating the situation. That since x is getting bigger and x is getting bigger, almost like look at the degree of the top and the degree of the bottom. But here we don't have a degree of the top because it's cosines and trig mixed with that monomial. But what we want to do to be proper here, even though I think it's going to end up being 1, I think I need to break this apart and consider 2 limits individually. Okay? We know that we can break apart this argument, the argument of the limit, into two separate fractions. That is, we could say this is equal to the limit as x approaches infinity of x over x minus cosine x over x. I just broke the fraction apart instead of having it combined. But now we can say this is two individual limits, the difference of two individual limits. So we can say this is the limit as x approaches infinity of x over x minus the limit as x approaches infinity of cosine x over x. Now, can we all agree that x over x, that's just a 1? So if that's just a 1, well, we know what that limit equals. The limit of a constant function is just equal to that number. So that's 1. Now, what is this limit here? So let's think about, again, this is just one of those simpler limits. Let's think about what's happening as x is getting bigger. I think this is pretty much the exact same situation we saw here. Cosine is ranging between -1 and +1, so it's bounded, but the bottom is unbounded. So as x keeps getting bigger and bigger, we're dividing a number between -1 and +1 on the top. We're dividing that by a astronomically big numbers eventually, and so that limit is 0. So my hunch was correct. My hunch was that this was 1 because it was dominated by these two terms, and we could look at the ratio of their leading coefficients, and it turned out that that hunch was correct. So again, this means there is a horizontal asymptote at y equals 1. Okay? So even though I don't know what that graph looks like, that's not something that's familiar to me, I know that there's a horizontal asymptote at y equals 1. And that's what this section is all about. It's about that missing piece. If we wanted to figure out all of the behavior of this graph, we would do things like take the derivative and find increasing and decreasing behavior. Look at the first derivative and find the relative minimums and maximums. We would then look at the second derivative, find the concavity. Well, over which intervals is this function concave up, concave down. And now we have the horizontal asymptote. We know there's a vertical asymptote immediately here, looking at the denominator, and a vertical asymptote at the origin at 0. And so putting all of this together, even though I have no idea what this graph looks like off the top of my head, we could get a pretty good idea of what it looks like just by looking at the analytical techniques that we have learned over Chapter 4. Okay, let's talk briefly about L'Hopital's rule. So that's the one thing I haven't talked about today thus far. L'Hopital's rule is really important. In fact, it's not even listed in this part of the chapter. I pulled this out of Chapter 8. You see here is Theorem 8.4. Now, that's not to say that we, obviously we're not going to Chapter 8 in this course. That's for one of your next calc classes. Okay, but L'Hopital's rule is still helpful to us here. What L'Hopital's rule, it's super nice. In fact, you would have loved L'Hopital's rule in Chapter 2 because L'Hopital's rule is all about making limits easier to evaluate. So whereas in Chapter 2 we had to do techniques like rationalizing a numerator, factoring and canceling out, all of that kind of stuff, L'Hopital's rule allows us to use derivatives to maybe simplify that process. That is, you only can use L'Hopital's rule in certain cases. Like here, we have L'Hopital's rule only works when you have a rational function, that is a fractional function, and you have different types of what are called indeterminate forms. Now, what's indeterminate form? Indeterminate form is when you look at the limit of the numerator and look at the limit of the denominator individually, and you get something like 0 over 0 or infinity over infinity or any of these versions down here. Now, there's other types of indeterminate form, but they're not. But we don't really need to worry about those right now because L'Hopital's rule works with the rational forms of indeterminate form. Okay, so if we say, let's take this rational function right here. we looked at that rational function. If you look at the limit of the numerator and look at the limit of the denominator, clearly the limit of the numerator individually is just positive infinity. It's growing without bound. Oh, sorry, we're looking at negative infinity here. So yes, it is, but it's still growing without bound. So the limit of the numerator here, if you start plugging in, it doesn't matter if they're negative, you're plugging in big, big negative numbers. The numerator is increasing in the positive direction without bound. Same thing with the denominator. If we plug in really big negative numbers, you're just going to make them raised to the fourth power. That's still going to be a very, very big positive number. So here, this is called indeterminate form, because when you look at the numerator by itself, you get positive infinity. And when you look at the denominator, you get positive infinity. So you're looking at the numerator and denominator individually. But here's what L'Hopital's rule says. L'Hopital's rule says if you get something like this, it's called indeterminate form, infinity over infinity, or if you get 0 over 0, or any of these versions with negative signs in them, then what you can do is take the derivative of the numerator, take the derivative of the denominator, and then try to find your limit again. And hopefully it's easier at that point. But guess what? If it's not easier again, if the function's still in indeterminate form, guess what? You can take the derivative again and then try again. You can use L'Hopital's rule over and over again, and hopefully you will get eventually to a function where you get the limit very easily. For instance, let me look at a rational function. I'll show you how this works. Now, to be honest with you, for a lot of the cases, L'Hopital's rule is just a way to verify the result that you already know is true. That is, if you're dealing with a rational function, L'Hopital's rule is only going to verify what you already know by looking at the leading coefficients. So let's just pick one out. Let's say we're going to do a rational function. Now we'll use this with trig and other transcendental functions, and L'Hopital's rule is going to be very helpful. But with the rational functions, it's just going to verify what we already know is true. So let's say the limit as x approaches infinity. Oh, let's just make it easy. Let's say 3x squared plus 2 over 2x squared minus 5. All right, or let's just say 5x to make it a little more interesting. There we go. Now we know that the degree of the numerator is equal to the degree of the denominator, so we know that the answer here is 3 over 2, the ratio of the leading coefficients. We've known that since algebra class, okay? But let's see here what L'Hopital's rule says. L'Hopital's rule says if you look at the limit of the numerator individually and the denominator individually, and you get something like infinity over infinity, which we do here. If we plug in a really big, if we look at the limit of the top individually, so you look at the limit as x approaches infinity of 3x squared plus 2, you get infinity. If you look at the limit of the denominator individually as x approaches infinity of 2x squared minus 5x, again, you get infinity. Those are just increasing without bound. Those are both parabolas, quadratic functions, and we know that they're going to be, if the leading coefficient is positive, they're going to be increasing without bound in the right-hand direction. Okay? So this is an indeterminate form. It is infinity over infinity. So L'Hopital's rule says, all right, if you have that happen, just take the derivative of the top and the derivative of the bottom, and then try to reevaluate your limit. See if you don't get indeterminate form. So what's the derivative of the top? Oh, well, we get 6x over, let's see, that would be 4x minus 5. And now let's try to reevaluate the limit again. Okay, well, the top is still approaching infinity if you look at the individual limit of the numerator. And the bottom is still approaching infinity if you look at the individual limit of the denominator. So it's still an indeterminate form. So L'Hopital's rule says, hey, just take the derivative again and try to reevaluate the limit. So we get the limit as x approaches infinity. What's the derivative of 6x? It's just 6. And what's the derivative of 4x? It's just 4. So now that's just a constant function. The answer is 6 over 4, which equals 3 over 2, which is the answer we knew it should be from the college algebra rational function technique. Okay? But that's how L'Hopital's rule works. Now, again, I have to caution you, it only works when you have a rational function and it's of the form 0 over 0 or infinity over infinity, or one of those versions with negative infinities. Okay? It doesn't work with any other forms, but it is super helpful whenever we are dealing with some trig functions. I'll show you how. Let's look at, or not even trig, other just transcendental functions. So I'll show you how this can be pretty useful. Let's see here. Let's find some nice trig ones. Oh, let's look at that one that we just looked at. Actually, that one from chapter 2. Let's look at that one from chapter 2 that we saw a lot, and let's verify our result from chapter 2. So in chapter 2, we looked, okay, actually this one right here. In chapter 2, we did this a lot. We looked at this limit right here. Instead of an infinity there, we looked at this. Now, L'Hopital's rule works with limits at infinity, or it works with limits as x approaches a finite number. So here, x is approaching a finite number, and L'Hopital's rule works. You just have to make sure you're in the correct form. Now, what happens if we try to directly substitute here? If we try to directly substitute, we get what? What's the sign of 0? It's 0 over 0. So we get 0 over 0 here if we try to directly substitute. Well, in chapter 2, we said, all right, let's try to rewrite this. Or actually, in chapter 2, we had to use the Squeeze Theorem to evaluate this. So instead of using the Squeeze Theorem every time, we just memorized that this limit was equal to 1. Now, let's say you forgot that, but now you have L'Hopital's rule up your sleeve. Okay, L'Hopital's rule says if you try to use direct substitution and you get 0 over 0, that's one of the forms that will allow us to use L'Hopital's rule. And in that case, all you have to do is take the derivative of the numerator and the derivative of the denominator individually the numerator, individually the denominator, and once you do that, rewrite your function and try to take the limit all over again. So what's the derivative of sine? It's cosine. What's the derivative of x? It's 1. Now I have to stress here, don't think you have to use the quotient rule here. We're taking the numerator derivative separately from the denominator derivative. So there's no quotient rule here. Okay? But now can we evaluate this limit? Can we use direct substitution, that is? I think so. Because what's cosine of 1? I mean, cosine of 0. Cosine of 0 is 1. So we get 1 over 1 equals 1. So instead of using the Squeeze Theorem, we had to draw a picture, we had to show graphically, we had to bound it, we had a circle, we had triangles. The Squeeze Theorem was certainly non-trivial to show why this limit was equal to 1. But L'Hopital's rule just allows us to show it's 1 in essentially 2 steps. One of those steps is this step is not necessary. It just allows us to find that limit immediately. Now, let me be clear. This is not a limit for in behavior. This is just a regular old limit, finite limit. This is not a limit at infinity. I just wanted to show you how L'Hopital's rule could really help us solve one of those chapter 2 type questions that used to be tough. Now it's not so tough anymore. Okay, let's look at some infinite limits and see how L'Hopital's rule could help us solve some infinite limits. Okay, let's look at an exponential, a modified exponential. Let's see here. Let's look at the limits. Limit as x approaches infinity of e to the x over x squared. Okay, now, I don't know what this looks like. It's an x squared on the bottom. We know what e to the x looks like as far as the graph is concerned. So this is growing without bound. X squared, what happens when you divide by x squared? Well, clearly that puts us a vertical asymptote at the origin, but as far as like what that graph looks like, I don't really know. But let's consider what L'Hopital's rule can do for us as far as the end behavior. Because off the top of my head, I really wouldn't know what this is doing. Because we have two functions that are growing, I don't know what's happening, which one's going to be bigger, you can think about it, I suppose, but just at first glance, I don't know what that graph looks like. So I don't know what's happening really far off to the right, that is the end behavior to the right. I don't really know what's happening in the end behavior to the left. So let's think about it though. Using L'Hopital's rule, is this in a form we can use L'Hopital's rule? What happens if you try to evaluate the limit of the numerator individually and the limit of the denominator individually? What happens if you just look at e to the x? As x gets really big, e to the x just gets even bigger. So we would say the top has an infinity. The limit of the top is infinity. Now what is the limit of the denominator? Well, if x keeps getting bigger and bigger, you just keep squaring it, it's also equal to infinity. So this is of the form infinity over infinity. That's called indeterminate. That's one of the types of indeterminate form. So that means we can use L'Hopital's rule. And L'Hopital says, well, take the derivative of the top, take the derivative of the bottom, and then try to reevaluate your limit. So we have the limit as x approaches infinity. Now what's the derivative of e to the x? Well, that's easy. That's just e to the x. What's the derivative of x squared? Just 2x. Okay, now let's try to reevaluate the limit again. Okay, well, we just talked about this. The limit of e to the x by itself is infinity, and the denominator by itself, the limit is infinity. So that's still in indeterminate form. That is, we can't really easily figure out what that limit is. So let's use L'Hopital's rule again and say this is the limit as x approaches infinity. Now, the derivative of the numerator, again, is just e to the x. But what's the derivative of the denominator? It's just 2. So now I think we can get a better idea of what's going on, because the denominator is a constant. So the numerator is growing without bound as x increases without bound. But what's happening with the denominator? The denominator is just dividing by 2. That's not really doing anything. Sure, it's having things, but if you raise if you raise e to the 10th power, then e to the 100th power, then e to the 1000th power, that's growing so astronomically fast, it doesn't matter if you're dividing by 2 or not. So we're going to say that limit is positive infinity, which means that's a special version of does not exist. That simply means the end behavior, as you're looking way off to the right of this function, way off to the right, it is increasing without bound. So you would say, if you were in college algebra class and you were asked what's the end behavior, you would say this. That is the right-hand end behavior, going up and to the right. Now, if you want to look at the left-hand end behavior, let's see what happens in the left hand. Okay? To do left-hand end behavior, what we have to realize is the only thing that really changes there is that we are looking at a negative infinity. So let's see here. Negative infinity. Let's see here. Limit as x approaches negative infinity. Oh, and then we have, let's see, we said e to the x over x squared. So same function. We're just looking at the left-hand end behavior. Now let's think to ourselves, is this in indeterminate form? If we're looking as x is getting more and more negative, what does that mean about e to the x power? If you raise e to the x, if you raise e to like the negative 10 power, the negative 20 power, the negative 100 power, the negative 10 million power, what's happening to the numerator? Well, think about your rules of exponents. What's e to a negative number? Okay, recall e to, let's say, negative 10, that's 1 over e to the 10 power because you have your negative exponents. So what does that tell us? That tells us as your exponent is a bigger and bigger negative number, the numerator is going towards 0. So I don't think this is going to be, actually, well, it might be if it's 0 over 0, but I don't think it's going to be 0 over 0 this time because we're going to have e to the negative power, because we're having a negative, plugging in negative x values, that limit of the numerator is going to be 0. But the limit of the denominator is going to be infinity. So that's not a form that works with L'Hopital's rule. So we can't use L'Hopital's rule. But lucky for us, this limit is not hard. Okay? Because if the numerator, if the limit of the numerator, so let's just write it out, the limit, because we have those properties of limits that says you can break a fraction apart and take the limit of the numerator and denominator individually. So if we have the limit of the denominator, excuse me, the numerator, over the limit as x approaches negative infinity of x squared. Oh, let's fix this. Which this is just properties of limits. Well, we know that the numerator, we just said that limit was equal to 0. Okay? But we're just going to be dividing by a bigger and bigger and bigger number. A negative number squared is just going to be a positive big number. But we're dividing 0 by a really big number. You're just getting 0. So the end behavior to the left is 0. Okay? So that means to the left, we're going to have end behavior that just looks like a horizontal asymptote at y equals 0. But to the right of this function, we're going to have increasing without bound behavior in the positive direction. So over here, we're going to have a horizontal asymptote behavior way off to the left. But to the right, we're going to have behavior that goes up and to the right. Now, I'm just curious at this point. Let's see what this looks like. So we have e to the x over x squared. And here we go. So again, I had no idea what this function looks like, but that basic analysis of the infinite limits showed me exactly what was true. If you look to the right, this function is increasing, if increasing without bound in the right-hand direction, but in the left-hand direction, it looks like there is a horizontal asymptote at the origin. And we already said that there's a vertical asymptote at the origin as well because we're dividing on the bottom by x. So we can get a pretty good idea of, of what the graph looks like before even doing the first derivative analysis and second derivative analysis. But first derivative analysis would tell us about increasing versus decreasing, and second derivative analysis would tell us about concavity, and of course we could find the maximums and minimums. So again, this is what the goal of this section is to just to give us an idea of the end behavior of these functions. Let's look at a couple more. Let's look at a log function. Okay, let's look at a log function. What about if we look at the limit as x approaches? Oh, let's see here what we have here. Infinity of natural log x over x. Okay, I think this is another one where L'Hopital's rule is going to be super helpful. Just thinking about this, I know what the natural log of x looks like. We've known since college algebra what that function, the graph looks like. It's increasing. It increases very slowly, but certainly it's increasing. And clearly x is increasing. We're dividing by x, but so there's an asymptote at the origin, but we're not looking at the origin. We're looking at right hand end behavior. So I guess the question is, what Is this in any type of form that L'Hopital's rule can help us? I think the answer is yes, because if you look at what's happening with the numerator as you're approaching infinity, it's approaching infinity itself. And now it approaches slowly. Okay, natural log of x rises very slowly, but it certainly is always rising. So that's approaching infinity. Now, x, clearly, if you just, as x approaches infinity, as you keep plugging in numbers, they're getting bigger and bigger. So this is of the form infinity over infinity. So we can use L'Hopital's rule, and L'Hopital's rule says, okay, take the derivative of your top, take the derivative of the bottom, and then reevaluate the limit. Hopefully it's easier that time. So what's the derivative of the numerator? Well, the natural log of x is just what? 1 over x. What is the derivative of x? Just 1. Well, that's nice, because this simplifies to the limit as x approaches infinity of 1 over x. So what is that limit now? That's really easy to think about. This, not so easy to think about. This, very easy to think about. What is happening to that fraction as x gets bigger and bigger and bigger and bigger? Well, clearly, it goes to 0. So this tells us that there is a horizontal asymptote at y equals 0. I wouldn't be able to look at that and immediately think to myself, oh, yeah, sure. There's a horizontal asymptote at y equals 0. Because that's not a common graph I'm familiar with. Okay? But a little bit of analysis with the aid of L'Hopital's rule allows us to find that rather easily. Okay? Let's see. Let's look at a couple more, just because I like L'Hopital's rule. Let's look at a couple more, and then we'll call it a day after that. So I think you get the picture. We're looking at limits at infinity. Those are going to tell us where the horizontal asymptotes are. And we're going to then use this stuff in our next lecture to be able to add this to our repertoire and be able to graph things by hand even more accurately, because we're going to be able to know the end behavior. We've always been able to find the end behavior of rational functions ever since college algebra, but now we're going to be able to find the end behavior of trig functions and other transcendental functions like logs and exponents and stuff like that. Okay? Let's see here. We've done e to the x over x squared. What if we have, on the other hand, what if we have like the power function on the top and the exponential on the bottom? Let's see what happens there. So let's see, what if we have a function like so? What if we have the limit as x approaches infinity of x cubed over e, oh, this is an interesting one, to the x over 2 power. Yikes. Alright, that's not so bad though, I guess. So we're saying, what is the right-hand end behavior of this function? That's what that limit is telling us. What does this function look like way over to the right as x increases without bound? Now, this is one of those, I think L'Hopital's rule is going to be a lifesaver. Because let's look at the limit of the numerator and denominator individually. Well, clearly, if you plug in, let's say, really big numbers for x, and you cube them, they get much bigger. So the top is going off to positive infinity. What's happening with the bottom? Well, if you plug in a really big numbers for x, divide them by 2, then raise e to that power, it's just getting bigger and bigger and bigger. So I think this is clearly in infinity over infinity form. So that is prime use for L'Hopital's rule. So L'Hopital's rule says, hey, take the derivative of the top, derivative of the bottom, and then try to reevaluate your limits. So we have 3x squared. Now what? Okay, this is a chain rule. Okay, so the chain rule says, okay, you just write e to the u, but then you have to multiply by the derivative of your inside function. So what's the derivative of x over 2? Don't do a quotient rule there. The derivative of x over 2 is just 1/2. So it's 1/2 e to the x over 2. All right, did that really help us out? Well, no, we're still in indeterminate form. We're still, if you try to evaluate the limit, you're still in infinity over infinity form. All right, well, let's try again. Let's use L'Hopital's rule again. All right, what's the derivative of 3x squared? Well, it's 6x. Now, what's the derivative of this again? Well, the derivative, let's ignore the 1/2 for a moment. The derivative of e to the x over 2 power is just the exact same thing we got, but we have to multiply by 1/2 again. So it's 1 over 4 e to the x over 2 power. Now let's try to reevaluate limit. What happens if we look at really large values of x? Well, the numerator is still going off towards positive infinity, and the denominator is still going off towards positive infinity. So we're still in indeterminate form. Use L'Hopital's rule again. And so we get the limit as x approaches infinity. Now we try to take the derivative of the top and the bottom. What's the derivative of 6x? Well, it's just 6. What's the derivative of here again? Well, you get another 1/2 factor. So we get 1 over 8 e to the x over 2 power. Now I think we might be good to go. Because what's happening on the bottom? It's going off towards positive infinity. What's happening on the top? Absolutely nothing. It's a constant function at 6. So if we take 6, then we're dividing by bigger and bigger and bigger numbers. What does this limit look like? Looks like 0. So that tells me that the end behavior way off to the right of this function, it might be crazy, to start with. If you look close to the origin, it might be crazy, who knows. But if you look way off to the right, this function has a horizontal asymptote at y equals 0. Alright, so the one last type of example I want to look at is what happens when you have like a radical as a part of your rational function. So we have maybe something like this. Let's look at the limit. Let's see here. The limit as x approaches infinity. Oh, let's pick one. Let's see here. 2x plus 1 over the square root of x squared plus 2. Now, I'm going to show you how to intuitively think about this. Then I'll show you maybe like a way to algebraically look at it. So like analytically look at it. Okay. So let's think about this. We had that, those guidelines for rational functions that said, if the numerator, the degree of the numerator is equal to the degree of the denominator, you do this. If the degree of the numerator is less than the degree of the denominator, you do this, and all that. Those 3 conditions. Now, I think what is important to understand here is that what is the degree of the denominator? Well, it's clearly the degree of the numerator. It's clearly a 1. Now, we don't talk about degree of denominator, or we don't talk about degree of radical functions, rather, because what's the degree of the square root of x squared plus 2? I don't know. Well, we don't talk about that. We talk about degree of polynomials. The top is a polynomial. The bottom is a radical function. Okay, but here's what you can realize. What is this bottom function, radical function, dominated by? It's dominated by the square root and then the x squared part. So what's the square root of x squared? It's like x, right? So this is behaving, the denominator is essentially dominated by the function x. That's what it kind of looks like. So you'd have 2x over x. So we would think, all right, that limit should be 2. Because it's almost like, even though there's x squared here, it's like we're taking the square root of x squared to get x. And then you have it's almost like, it's not really proper to say this, but then you have the degree of the numerator equals the degree of the denominator. So you take the ratio of those two numbers, 2 over 1, you get 2. Okay? Now, here's how you would do that analytically. Okay? Analytically, you would say, okay, we want to divide by the highest power of x. We want to divide every term by the highest power of x that we see. Now, ignoring this, how do we divide by the highest power of x? Well, I see the highest power of x here is a 1, x to the first power. So if I divide everything by a x, that is, divide every term you see in that function by an x. So we're going to take the limit as x approaches infinity. Now we're going to have it's going to look really crazy for a minute. What happens if we divide everything by x? Well, you get 2x over x plus 1 over x. Now here's the kind of tricky thing. How do I divide the bottom by x? Okay, so I'm going to do this, x squared plus 2 over x. But that doesn't, that just looks like a bunch of gibberish to me. We have to figure out how to rewrite the denominator. Okay, how do we rewrite this denominator so that it's one item instead of a radical function over x? Well, here's how you do it. Okay, you have to realize your rules of radicals. Okay, what's 2x over x? That's just 1, right? Nope, that's not just 1. That's 2 plus 1 over x. Now, in order for us to rewrite this denominator, we have to have a square root. Like, the rules of radicals say, if you have, a square root divided by a square root, you could write that as a single square root. Okay, but now we have a square root divided by a not square root. So how do we make a square root but not change the value of x? We'll do this. Make it a square root of x squared. That's x, right? But now we can combine the denominator and say this is the square root of x squared over x squared plus 2 over x squared. Okay, now let me rewrite that radical sign. That radical applies to the entire denominator. Okay, but now let's think about what's happening here as we take that limit. As we take that limit, what happens there? That goes to 0. Okay, that stays the same. What happens here? That goes to 0. But what's x squared over x squared? That's just 1. So what's the square root of 1? It's just 1. So our solution here is you have 2 over 1 is 2. Oh. 2 over 1 which equals 2. Which is exactly what I said it should be just by thinking about it. That is thinking, okay, the square root of x squared is basically x. 2x over x gives you 2. Okay, I'll do another example just to round this off. But what we tried to do there was to divide everything by the highest power of x. Let me pick maybe a little more interesting one. Let's do the limit. Let's look at the limit as x approaches negative infinity this time. Oh, let's see, the square root of x to the 4th minus 1 over x cubed minus 1. Okay? Now, I'm thinking here, and this is just my initial thoughts, that if you think about the numerator, you have this, it's dominated first of all by x to the 4th, but then the square root. The square root of x to the 4th is x squared. So for all practical purposes, the top is just behaving like x squared. The bottom is behaving like x cubed. So we say that we would say that the top is of lesser degree, kind of in some sense, than the bottom. So our guidelines for rational function limits say that this limit should be 0, because the top is growing at a slower pace than the bottom. Now, let's see how that works, but we need to show that algebraically, analytically. So let's divide everything by the highest power of x that's not in our radical. Okay? Again, just like over here, we divided by everything by x. Let's divide everything by x cubed this time. Every term. So we're going to say the limit as x approaches negative infinity. Now, let's see here. We're going to divide the top. So x to the fourth minus 1. We're going to divide it by x cubed. That's the harder part. And then we're going to divide every term on the bottom by x cubed. So x cubed, this is the easy part, x cubed over x cubed minus 1 over x cubed. Now recall, okay, this is going to take a little bit of work on that numerator. This is the limit as x approaches negative infinity. All right, now, let's start the denominator first. X cubed over x cubed, that's easy. That's 1. 1 over x cubed is just 1 over x cubed. Nothing to do there. Now, we want to combine the top into a single radical, just like we did in the previous exercise. Now, we need to have, to do that, we can't just combine an x cubed and a square root. We have to rewrite that as, let's just do that right now. Since we have here, we can erase. Okay, we want to divide by x cubed, but we can rewrite x cubed as the square root of x to the sixth. And now we can combine those two square roots because of the properties of radicals, and I can rewrite this as a root. Okay, I'm going to have, let's see here, x to the fourth over x to the sixth, and I'm going to have minus 1 over x to the sixth. Okay, now what's x to the fourth over x to the sixth? Let's think about that. All right, x to the fourth over x to the sixth, rules of exponents say that's 1 over x squared. So let's rewrite this as 1 over x squared, just to save a little bit of room here. 1 over x squared. Now, let's think about what happens as x increases without bound in each of these individual situations. As x increases without bound, what happens here? 1 over x to the sixth, that goes to 0. What about here? 1 over x squared, again, as x is getting really big, that goes to 0. What happens here? 1 over x cubed, that goes to 0. So essentially we're left with 0 minus 0, or 0 over 1 equals 0. And there you go. So if you have these radicals mixed with rational functions, you can kind of think about it. Like over here we said, okay, that's basically like x squared over x cubed, so it should be 0. But we do need to verify that algebraically, analytically, using the limits, okay? Okay, so even though we can justify it, conceptually, we still need to show it, and we do that by dividing by the highest power of x. Now, you don't choose the highest power of x that if it happens to be under your radical. You choose the highest power of x that's not underneath your radical and divide every term by that highest power of x, okay? So, let's just recap. We've been talking about end behavior. So this tells us that there is a horizontal asymptote at y equals 0. We have a lot of those. We have a lot of horizontal asymptotes that pop up at the origin, just like we have a lot of asymptotes for vertical asymptotes that pop up at the origin. But we also saw, here we have like a horizontal asymptote at 2. We saw, other horizontal asymptotes at different values at 5 and something like that. But the point of this entire lesson was to find the end behavior. Okay? Sometimes end behavior was really easy to come by. And so all we had to do, was look at, if the function was getting really big on the denominator and constant on the numerator, and then the end behavior was 0. That is, the horizontal asymptote was 0. Sometimes the limit was infinite, which meant that there was no horizontal asymptote, at least in the negative direction. And so the limit to the left was going off, the y values to the left were going off to, in this case, to negative infinity. So here we had a horizontal asymptote of 1/2. This is all about what the end behavior is. So this is telling us what's happening really far off to the left of a graph, or maybe what's happening really far off to the right of a graph. That is the limit as x increases or decreases without bound. We also had L'Hopital's rule that helped us out with like some of the trig limits, especially. L'Hopital's rule wasn't particularly helpful with the rational limits because we know how to deal with those in an easier manner. But L'Hopital's rule really helped us out with those trig limits when they were in either 0 over 0 or infinity over infinity indeterminate form. Okay? And of course, this is all just about horizontal asymptotes. So, limits at infinity. Limits at infinity can be infinite or they can be finite. Here's an infinite limit at infinity. Here's a finite limit at infinity. Finite limit at infinity. But if you get an infinity for your answer, then that's an infinite limit at infinity. Alright, hope this has been helpful. We will use this stuff in our next lesson as we go to graph just oddball functions that we have no idea what they look like. We're going to use the end behavior in conjunction with everything we've done thus far to be able to produce nice looking graphs. Alright, that's a big part of Calc 1 is being able to develop a nice intuition for how graphs look. So this is a really important part of Calculus 1. Hope this has been helpful. You can always shoot me an email if you have any more questions, and I'll be glad to help you out.